Okay, for section 2, we're going to discuss instantaneous velocity, and I'm actually going to spend a lot of time going over some basic calculus concepts. So in the first section of the book, we talk about average velocity, right? In average velocity, we put V average is equal to the total change in the distance or the displacement over the total time. That gives us an indicator of, well, if we're, I guess one example is if we have a velocity that stays constant the whole time, then what that's going to equate to, so if this is velocity and this is time, we would have a position here and a time, and this is a constant slope, right? So basically, if we take what we're finding here is we're finding the change in the rise. So the rise over the run. Hopefully you're familiar with that concept. I guess in this case we'll call the run the delta t. So that's really what we're doing here, is looking at the slope. Now, when we're talking about instantaneous velocity, that's a little bit different. And instantaneous velocity is, well, okay, maybe we have a position that changes with time, but it's kind of all over the board. Maybe they go this way and then they go up, that sort of thing. So it changes. And if we take an average, we can kind of approximate that. If we're looking at the average velocity, we would approximate it as something like that line. But what if that's not what we want to know? We want to know the velocity at this particular point. We'll call this t1. How do we find that? And that's kind of the idea behind instantaneous velocity, is we can look at the velocity at a particular moment in time and not have to look at the overall velocity. Well, in order to do that, there's a lot of ways to think about this, but basically when we're finding a velocity, we're finding a change with respect in position with respect to time, right? Well, what if we want to know the velocity at this point? We can try to find the slope of this line right here, okay? So we can do that for all these little pieces of time, and then we'd be able to figure out how to do that. Well, mathematically, we want to figure out how to do that. That's a little bit tougher. So what we do is we employ something called a derivative, which I'm going to kind of go over basically here so that you'll have a good handle on it. And basically we say, well, the velocity is the change in position over the change in time. That's still true. Okay, that's a rate of change of position is what velocity is. Okay, so how do we find the slope of that little bit? Well, let's take a graph, for instance, and we want to find, we'll call this t naught. We want to find the velocity of t naught. Well, what we could do is we can imagine finding this tangent line, except we don't know how to find the slope. On the other hand, we could take a secant line like that, and let's go ahead and say that this is time t1 and this is time t2. Now, this line is parallel to that line. And so what we're going to do is we're going to imagine taking that line and moving it down to this line. And mathematically, we're going to define this using a limit. So we're going to say that the change in position over the change in time is equal to the value of x at time t2 minus the value of x at time t1, so that's a delta t, right? So we're looking at this point here and this point here, and then we want to look at, for a change in time, that's going to be t2 minus t1. Okay, that makes sense for our secant line. So I'm going to just make a little substitution here. Some of you will be familiar with this, but if not, I'm just going to do this to kind of help explain, make our calculation simpler is what I'm really doing. And I'm going to say that delta t, which we have as being equal to t2 minus t1, is actually equal to this value h, okay? And I'm going to say that t2, which is the value here, is actually equal to t1 plus h, okay? So now I can rewrite my average velocity equation, and I'm going to call this x at t2, which is actually x at t1 plus h, right, minus x of t1, so that's the same, over, well, I'm just going to put h in there instead of t2 minus t1, okay? And as we move this line down towards the value where it actually becomes a tangent at t naught, what we're doing is we're making h smaller, okay? So make h small. This will hopefully look familiar, and those of you who aren't familiar with calculus or haven't seen this yet, hopefully you'll see it fairly soon. What we're going to do is we're going to say that this delta x over delta t, we're going to redefine this as dx over dt, where d means we're looking at an infinitely small value of delta. So delta x in this case can change a lot. When we put the d there, basically that means the change is going to be so infinitesimally tiny, right? And then this is going to be equal to the limit as h goes to 0. So basically this change as we move that line towards t naught is going to become very, very small. It's going to get shorter and shorter and shorter till right here where it's just a point. Okay. Limit of x at t1 plus h minus x of t1, okay, and that's h. Now as we move that line, remember t1 is going to move closer and closer to t naught, so I can actually rewrite this as dx dt is equal to the limit as h approaches 0 of x of t naught plus h minus x of t naught, okay? So this is going to give us the value of the slope of that line, of that tangent line, at t naught, and that will tell us our instantaneous velocity. So this is what we call that's what we call v of t naught in this case. Okay, so all right, so we've got, let's look at this. What happens as h goes to 0? Well, as h goes to 0, this will go to infinity unless there's some way to cancel out h. So I'm going to kind of give you an example of a problem. So let's look at, let's imagine that our equation for our position, so x, that's our equation for our position, is going to be equal to 5t squared, okay? So let's plug that in. So we're going to have v of t is equal to the limit as h goes to 0 of x of t naught, well, we'll just put t, plus h minus x of t, okay, over h. So limit as h goes to 0. What we're going to do is we're going to substitute this equation in for here, for this. So we're going to have 5. Now t is going to become t plus h, and we're going to square that, right? Minus x of t, well, x of t is just 5t squared. Okay, all of this will be over h. We're going to multiply that out. So we've got 5t squared plus 10th plus 5h squared minus 5t squared over h. Well, the 5t squared terms are going to cancel, right? Okay. Limit as h goes to 0 of 10th plus 5h squared over h. We can simplify this further by dividing by h. So that gives us 10t plus 5h. Now we're going to employ this limit and we're going to say, okay, h is equal to 0. If h is equal to 0, we're basically left with 10t. Okay, so that is our instantaneous velocity for that equation. And we can plug in a value for t naught to figure out what it is exactly at a particular time. So this would give us, you know, some sort of curve, and depending on if we stuck in the value for t1 or t2, we would know exactly what the slope is at either of those points. Okay, now fortunately there's an easier way to do this. If somebody noticed a trend in all of this, and so we use a different, if we're using a polynomial, so polynomial, of course, if you hopefully remember, is going to be any equation where it's of the form where it has powers. So you would have like ax, I don't know, to the n plus bx n minus 1 until you get to some value, we'll call it q, and then this will just be a constant. You know, you'll have q, and then the previous one will be times x, and then x squared, all that sort of thing. So polynomial has a real simple form for a derivative. We write this as, in this case I'm writing it, the equation u instead of x. Well, no, let me write it as x. X will have the form of c times t to the nth power. Okay? That means that the derivative of x with respect to time is going to be equal to n, so we're going to multiply times that power. We're going to keep that constant, and then we're just going to reduce the power by 1. Now if we go back up to our previous example, remember our equation was 5t squared, right? Let's try that. dx dt of 5t squared, okay? So our n is going to be 2, so we're going to have a 2 in front. Our c is equal to 5, so we're just going to keep that 5 there because that's the c. And then we're going to have t to the 2 minus 1. Well, this ends up being equal to 10 times t. But that's exactly what we got using the limit. This is a lot easier to use, though, okay? So what I want you to remember specifically is that when we're doing these with polynomials, when we find a velocity, an instantaneous velocity, that's basically the same thing as finding a derivative. We're going to take the derivative of the function in order to find a velocity, because we're trying to see how much that function is changing, and a velocity is a rate of change of position. So it's the derivative of the position. Okay? All right, now I'm just going to make a note. There are some other special derivatives that are good to know. I think they list this in the back of your book or something like that, but these will come in handy in the months ahead, so you probably just want to write it down someplace, like in the front of your notebook or something like that, and keep it. So if we have a function, we'll call it f of t. The derivative is sometimes denoted by f prime of t, so this is the same thing as df dx, or dt. Okay, so that's what that means. So we just kind of talked about it. If we have ct to the n, the derivative, of course, is nct to the n minus 1. All right. If we have a sine function, sine of t, the derivative of that is cosine of t. If we have cosine of t, the derivative of that is minus sine of t, and that minus sign does become important. Okay, I'm going to continue my table down here because I ran out of room on that other line. The tangent, the derivative of the tangent of t would be the secant squared of t. The derivative of the exponential of t, well, that just ends up being the exponential of t. And there's a really bad joke I can tell you at some point. Remind me. The logarithm of t, well, the derivative of that just ends up being 1 over t. So those are handy things to help you understand when we're doing the math behind finding an instantaneous velocity. We have to take a derivative, and depending on the function, you probably want to use one of these tables, or use a table or one of these functions. Most of the time, however, we're going to be dealing with polynomials, so that's one you probably just want to go ahead and memorize.